Hey, let's work through, this is worksheet number 4, homework number 4 over curve sketching, derivative graph, and some particle motion. We're going to start with a little bit of a graph recognition here. So number 1, it says the graph figure above shows the graph of f on the interval from a to b. Which of the following could be the graph of f prime, which is the derivative of f on the interval from a to b. So we're trying to match a derivative graph. So I think the best thing to do is, or the most structured way I can think about going through this is, let's gather information that we know about this graph, right? Where are the maxes? Where are the mins? Where are the POIs? And let's create a slope or a concavity sign line, and then from there we can decide based off of the sign line which is the best match for our derivative graph. So I think the max and mins are easy to find. This is the original graph, so wherever we see our max and mins, that's going to be where where we expect them to be is very straightforward. So that's our max. We got relative min there. We have relative max there. But I also want us to be able to pick out points of inflection. So just as a reminder, points of inflection is where the concavity changes, right? So if I can imagine my graph being concave up, and then at some point it changes to concave down, that transition point is called the point of inflection. And then in this graph here, concave down to concave up, that's another transition point. So that's a point of inflection as well. So I think we kind of, it's more subtle here, but we can see that there's a point of inflection across these graphs here. So you see how the graph kind of has that upward opening up curvature, but then it's going to eventually change to that concave down, right? So there's that transition point somewhere. I'm going to call this a POI. Okay. And then from concave down to concave up, there's got to be another POI somewhere here. Okay. We don't know the exact value, but at least we have some idea, right? It's got to happen somewhere in this region. And then from concave up to concave down, there must be another point of inflection here as well. And then this is kind of subtle here. You see how this is concave down, but you see how there's a slight, it doesn't go all the way up, but it does begin to kind of exhibit that concave up shape over here. So I'm going to call this another POI. Okay, so these are more subtle, but we can kind of visualize, even though it doesn't fully complete concave up, it is a portion of the concave up graph. So that's enough for us to know there's a transitional POI there. I'm just going to assign numbers just to make it easy for me to plot them. So let's say this is at -1. Let's say this is at 1. Let's say there's a relative max at 1. Let's say there's a POI at 2. There's a relative min at 3. There is a POI at 4. There is a max at 5, and then there is a POI at 6. Okay, just so I can have some reference point as I create my slope and concavity sign line. Okay, so here's my slope sign line. I'm going to extend from A all the way to B, and I know that I'm targeting max and min. So I have 1, 3, and 5. The rising and falling is just going to be based off of what I see in this graph. So the graph is going to fall, then it's going to it's going to rise, then it's falling. Relative minimum rises after that, and then falls after that. We can also create a concavity sign line here. Again, we're stretching from endpoint to endpoint. And POIs, I say, was that we said was -1, 2, 4, and 6. Okay, so this is concave up, concave down, so it's going to keep transitioning back and forth. Now, off the derivative graph, we know that a derivative graph is going to have x-intercepts as where slope is 0. All right, so we're looking for x-intercepts at -1, 3, and 5. Sorry, at +1, 3, and 5. So we're looking for 3 x-intercepts. There's only 2 x-intercepts here. There's only 2 x-intercepts here, so I know that A and D are already out. And then points of inflection, the way that these are going to appear on a derivative graph is from the peaks and valleys. Okay. Hey, Sam, how are you?
Doing well.
Yeah, I'm just going through this review here, but feel free to ask questions or anything that's, yeah, anything that's on your mind. Okay, so I have peaks and valleys. So the way I identify points of inflection on a derivative graph is from the peaks and valleys. So I know there must be a peak and valley at -1, 2, 4, and 6. So I should be counting 4 peaks and valleys. I'm only down to these 2 options here. Here I only see 2 peaks and valleys, but here I see the 4 that I need. 1, 2, 3, and 4. And that matches nicely with the points of inflection, along with 3 x-intercepts. So our B is our best option here. Okay. So I said on my key here, there are 4 points of inflections because we have 4 peaks and valleys, and then 3 relative extrema. So therefore 3 x-intercepts. 1, 2, 3. Yeah. All right, number 2. In the xy plane, the order pair 0, -2 is on the curve. If dy dx is equal to 4x over 9, which of the following statements is true? Okay, so at these order pairs, there's a relative minimum because dy dx equals 0 and the second derivative is greater than 0. So this is applying a little bit with second derivative test. So I think we can have a better idea as to what's happening if we can just go ahead and find the values, right? So we can find, we can evaluate the order pair into dy dx to find the slope, but we can also find the second derivative, evaluate the point at second derivative so that we can have a better understanding as to which of these options is suitable. So to start off with the easier path here, if I just enter in 0, -2, and for dy dx, I should be able to quickly know whether I'm matching this option here. So I'll put that over here. So I know that dy dx at 0, -2, my slope at 0, -2, I'll replace 0 in for x, -2 in for y. I get 0 over -18, and that's just equal to 0. So my slope is 0, and that's what all my choices are showing me. Okay, so that's consistent. Second step, though, let's go ahead and find the second derivative so that we can actually evaluate the second derivative and have a way of determining which option to choose from. So if I want to find the second derivative, let's see, dy dx is 4x over 9y. If I want to find the derivative from this point, I have to go through quotient rule. And then when I go through quotient rule, there's also a little bit of implicit because I got to involve dy dx for y's derivative. So I'm going to give the notation for the second derivative, d2y over dx2. So I know that I'm going to treat the top as the f, and then I'll treat the bottom as the g. Right? So here's quotient rule. Right, I'll find each of the derivatives here. F prime, so 4x becomes 4. The original g function is just the 9y, no changes. Back to f. And then g prime, we got to ask the derivative for 9y. So 9y becomes 9, but we're asking for y's derivative, so we need to attach a dy dx. All over my denominator squared, so 9y quantity squared. I'll go ahead and replace every x and y with 0 and -2. 0 in for x, -2 in for y. Because eventually I have to be able to know how to interpret that. Okay, so 4 times 9 times y, which is -2, minus 4 times 0 times 9 times dy dx. And my dy dx at that point in time is 0. We found that already. So it's going to wipe that second term out all over my denominator squared. 9 times y. So 9 times -2, that's -18 squared. So I'm left with 4 times, I know that this second portion just goes away. That's just -72, right? Divided by 18 squared. And that's just going to reduce down to -2 over 9. So I know that my second derivative at 0, -2 is equal to -2/9, which is less than 0. Okay, so we can narrow down our options, right? All these are zeros for slope, but only a couple of these have a negative concavity, negative second derivative value. So we know option, this one is not right here. So we're only down to B and D. Okay, B and D. So let's see what information we have. We know the slope is 0, and we know the second derivative value is negative. So let's gather that information here. We know that for this graph, the slope at 0, -2 is 0. And then we also know that the graph is concave down because we're getting a negative value at x equals 0. So if we can imagine these two information pairing together to be part of the same graph, then imagine a graph that looked like this, 0, -2. We know there's a slope 0 at this point and it has to be part of concave down graph. So the only way that we can have a slope 0 and concave down is if the graph actually looked like this, right? And if the graph is concave down with the slope 0, we can conclude that point must be a relative maximum. And this is application of the second derivative test. And B is relative min, D is relative max. So relative max is a better option for us. Answer choice D. Next page. All right, number 3, the first derivative of the function is given as f prime. What's the coordinate, x coordinate of the inflection point? So we know the inflection point has to come from the second derivative, so we're going to have to make our way down to the second derivative. To get to f prime, f double prime, though, I have to involve product rule because I have 2 portions here. F and G. So I'm going to spell out product rule here. F prime times G plus F G prime. F prime, x cubed plus 2 just becomes 3x squared. E to the x, we keep that original G function. We keep the original F function. And in G prime, the derivative for e to the x is just e to the x times 1. So just e to the x. So we want to know, when is there an inflection point here? We have x cubed, x squared. It's going to be tough for us to go through any factoring step. So I think the best thing to do is let's just plug this in the calculator and see when, see if it actually hits 0. And if it crosses the x-axis in a way where there's a change in sign at that x-intercept, then we know there must be an inflection point there. So we're going to look for an x-intercept, but we're also going to make sure that there's actually a change in sign. So it's got to cross over the x-intercept. Basically, right now we're looking to see when is f double prime equal to 0 and seeing if there's a change in sign. So I'm going to graph this. You can also go through numsolve and find that value, but I'm going to graph. I'll do zoom 6 just to get a standard window here. And I look at my option choices. So this is helpful. We know that we're looking for values somewhere between -4 and 0, right? So you know it's going to have to land somewhere in that region. All right, so there's my x-intercept. And I see the graph is crossing from negative to positive. So that indicates that I'm starting with a concave down, ending up above the x-axis, concave up, and across the x-axis. So that must be a point of inflection there. So I'm going to do a little bit of zoom in, zoom box, just so I can look a little bit closer as to what's happening at that point. Oops. Try again. Zoom box. So I just want to look at this region to see where that x-intercept is. Hit enter. Okay, we have a better picture here. If I do second trace, looking for 0, I'll choose a point on the left of the x-intercept, hit enter. I'll scroll over to a point on the other side of the x-intercept, hit enter. And the calculator should find that x-intercept for us. -3.196. So we see that there's a critical point at -3.196 to the left, is below the x-axis, to the right is above the x-axis. So we can confirm that, yes, it goes from concave down to concave up. There must be a POI at this critical point. Yeah, numsolve can also do this for us. We just enter this in. On one side, set equal to 0, solve for x, and then we can start at any value near these points, and this should be able to identify that negative 3.196 as well. Okay, number 4. Our function is twice differentiable, so that means that the slope exists, concavity exists, it's a smooth curve all the way through, and we have our function order pair, f of 1 equals 7, f of 3 equals 12. Maybe it's helpful if I can just kind of sketch this graph out, just to have some reference point, some visual for what's happening here. So we know that the graph is always positive slope, but always concave down. So positive slope, concave down. So the graph is only going to have this shape, right? So technically it shouldn't even level off, so it should just continue rising. But it's going to just always have, it's always going to maintain this shape basically. Right? It's always rising, always concave down, so it's never going to flatten out, but it's just going to keep continuing in this curvature. Okay. So it says, which of the following could be a possible value for f of 5? So we know that f of 1 is equal to 7. We know there's order pair of 1, 7 here, and we know there's an order pair of 3, 12. Now let me put this over here, 3, 12. So what could be a possible value for 5? Basically, that's what we're trying to achieve there. Okay. So we do know that each of these slopes should be positive, right? So the slope between these 2 points has to be positive. Slope between these two has to be positive because it's always going to maintain that positive slope all the way through. But here is what we need to also be able to understand is that each of these slopes between these order pairs is going to keep decreasing, right? So maybe this is a slope of 3, then it's got to go to like 1.5. Then it's got to go to 0.5. Then it's got to go to, 0.25. So the slope, each of these consecutive slopes have to keep decreasing because we have to maintain that concave down shape. So the idea is that, well, if I can figure out the slope between these 2 points, I know that whatever I get as a result of this positive slope has to be less than what I have here. So let's figure out what the slope is between these 2 endpoints, right? It should be positive slope. So let's see here. The slope here is 12 minus 7, change in y, over the change in x. So I get 5 over 2, which is 2.5. So if the slope between these 2 points is 2.5, then the slope between these 2 points has to be less than 2.5, right? If it's not less than 2.5, then we're not maintaining the property that they're giving us. So whatever the slope is between these 2 endpoints, or between the next 2 order pairs, well, first has to be positive, but it has to be less than 2.5, right? And the progression of the slope has to keep decreasing. while still maintaining a positive value. So we have a couple of options. It's either going to be 16, it's going to be 17, 18, or 19. So let's test a couple of points here. Let's start with 16. Let's say I want to test the order pair between 312 and 516. Okay. So between these two order pairs, my slope is going to be change in y over the change in x. So 4 over 2, that's equal to 2, and that's consistent. These two order pairs is producing a positive slope that we want, but it's also producing a slope that's less than 2.5. So this should be the answer, right? And I want to show you that if I try other order pairs here, that we're not going to get something that's less than 2.5 anymore. So if I do change in y over change in x, this is equal to 5 over 2, which is 2.5. So it's not decreasing. If my order pair is 517, then my slope is maintaining a 2.5, and we know that can't be true, right? If it's truly concave down, my slope has to continually decrease. So if 17 is already producing 2.5, then I know 18 and 19 will just be something even larger, which is not going to hold. So the only order pair that's going to maintain that relationship that we need in terms of concavity, it's going to have to be A. Okay. That was something that other students had questions about. Sam, does that make sense? I don't know if that was a question that you had about this worksheet.
My question was mainly on number 3, but I think you covered that pretty well. So.
Okay, good. Yeah, thanks for letting me know. Number 5 then. We have our graph y of x. It's asking, it was telling us that there's a point of inflection at 2, -2. And we know the point of inflection has to come from the second derivative. So we have to make our way down to, we have to get to f double prime in order for us to have something to work with. So I'm going to make my way down to the second derivative. Remember that a and b are just constants, so we have to treat them like if it was like a 3 or a 5 or 8 sitting in front of these x's. So my derivative, a is the coefficient, just going to stay with my derivative, so I'll bring the 3 down, so 3ax squared. 6x squared becomes 12x, bx becomes b, and then -4 goes to 0. All right, moving on to the second derivative. Power rule, bring down the 2, we get 6ax minus 12. 12x becomes 12, and b goes away to 0. Now, if there's a point of inflection at 2, -2, what that means is that I can plug 2 in for x, and I should be able to set my y double prime equal to 0. So point of inflection is where y double prime is equal to 0. So I'm going to set y double prime equal to 0. I know the x value of my point of inflection is 2. So if I can insert 2 in for x and 0 in for y double prime, I should be able to solve for a. And that will help me make progress in my goal to try to get to a plus b. So replace the y double prime with 0. My x value at that point is 2. You can cleanly solve for a here. Move to 12 to the other side. 2 times 6 is 12. So a is equal to 1. Okay, so we have a figured out. The derivative is not really going to help us much because we don't have information about the derivative or about the slope, but we do have the y value. We do have a y value that is coming from the original function. So what if we go back to the original function, because we know the y value, we now have a, we have x. So if we have our y value, our a value, and our x value, we should be able to isolate and solve for b. Right? So I'll write the equation again, ax cubed so my y value I'll replace with -2. My a value I'll replace with 1. X I'll replace with 2. Okay, do some cleanup here. 2 cubed is 8. 6 times 4 is 24. Eight minus 28 is -20. Oh wait, that should be 24. $18 equals 2b, so b is equal to 9. So I have my a value being 1. I have my b value being 9, so therefore a plus b must be 1 plus 9, which is 10. Okay, number 6. A particle moves along the x-axis so that at any time t, its position is given by x of t. What's the velocity when its acceleration is 0? So we're just going to find velocity and acceleration and use them accordingly. So let's find velocity function. Sine becomes cosine, so 3 cosine of t. T squared becomes 2t, and then 7 goes to 0. My acceleration function is second derivative, so find the derivative of velocity. Cosine becomes negative sine. 2t becomes 2. All right. Okay, it says, what's the velocity when acceleration is 0? So I'm going to set acceleration equal to 0, solve for t, and then plug that t value into the velocity function to figure out the velocity. This is a calculator question. I can use numsolve basically to find that x value. Now, acceleration is going to be 0 at multiple points. So I think maybe the better expression here is what's the velocity when acceleration is first equal to 0? Because it's going to hit 0 multiple times because of the way the sine graph is going to be. But we have answer choices here to kind of help us focus our potential points here. So if I do numsolve, Bradian mode, So if I start at 0, I should be able to arrive at an answer choice that's within the range. So I have t is equal to 0.729. Okay, so that's close to 0. That means that we have an acceleration, a time value when acceleration hits 0 at a point that is close to our starting point. So now that's not our answer because this is a time when acceleration is 0, but we're asking for the velocity at this time. Okay, we're asking for the velocity at this time. So it's a two-step process. First, we have to figure out the time that's appropriate, and then we're going to enter that time into the velocity. So now we can find the velocity at this moment in time. So just replace 0.729 in for the t's of my velocity function. And then just enter this in the calculator. And that is going to result us with 3.696. Okay, number 7. We have a second derivative given by f double prime. So this is the second derivative function here. For what value does the graph have a point of inflection? So if we're looking at the second derivative function, it's good to just label what we're dealing with. Anything above the x-axis is going to represent where my original graph is going to exhibit concave up. Anything below the x-axis is going to be where I'm going to experience concave down. Anything on the x-axis, these are potential POIs, but only if it crosses the x-axis, right? It's got to change from one concavity to the next. So we have a couple of x values, x-intercepts that actually cross over the x-intercept. So we have one here, we have one here, but careful, this is a critical point, but it's not a point of inflection because the sign doesn't change. So if we were to look at this from a second derivative sign line perspective, we know that at A and 0 and E are all critical points, but to the left of A, graph is concave down. Between A and 0, it's above the x-axis, so concave up. Between 0 and E, it's below the x-axis, so concave down. But then from E onward, it's still below the x-axis, it's still concave down. There's no change in sign. There's only change in signs at A and 0. So our answer choice is D. Okay. All right, Sam, any questions? You're good?
Just for that number 1, did you just use like sample numbers?
I did, yeah. I just use sample numbers just so I can have some way of marking my graph. Otherwise, I guess if I could have used like letters, but it just seems more intuitive just for me to use numbers. Yeah, so I'm just picking numbers that are not necessarily true, but it's enough for me to at least have some anchor to match with my graph, since those points are not identified on this graph. Okay, still have any questions about number 1?
Number 1 is good. For number 4,
Mm-hmm.
are we assuming that it's at 16 because that's the only number lower than 17.
Exactly. Right. 16 is the only number that's going to give me a slope anything less than 2.5. 2.5 is not good enough. If I try it at 18, I'm going to get like 3. If I try it at 19, I'll get like 3.5. So the only thing that's going to maintain that ability for me to get that concave down, that reducing of my slope value, it's got the only choice is 16.
So if this were like an open, could this question be an open-ended problem?
No, it couldn't be. This would have to be a multiple choice question.
Okay, that's it. Thank you.
Yeah. Okay, so I'll be back at 1:30 for the going over worksheets 5 and 6, and then 2:30 for worksheet for the AP review homework number 7. So um, maybe I'll see you then.
Awesome. Thank you so much.
All right, thanks, Sam. Bye.